Let us continue dipole moment. Now we will take a benzene we have taken. Now let us replace one hydrogen by Cl. Let us replace this hydrogen by Cl. So we will get a chlorobenzene. We got chlorobenzene we got. Let us replace this hydrogen we replaced by chlorine. Let us replace this hydrogen by chlorine. So what we will get, we will see. We got a so and so. This is a dichlorobenzene. This is a dichlorobenzene. Instead of this hydrogen, let us replace this hydrogen by Cl. So we will get dichlorobenzene. Instead of replacing this hydrogen, let us replace this hydrogen by Cl. So we will get a dichlorobenzene like this. Now this chlorine present at first carbon, this chlorine present at second carbon. Therefore, we can call this is as a 1,2 dichlorobenzene. Otherwise, we can call this is as ortho dichlorobenzene. We can call ortho dichlorobenzene. We can say this one. This chlorine is attached to first carbon, second carbon. It is third carbon. Therefore, it is 1,3 dichlorobenzene. Otherwise, meta dichlorobenzene or M. Like this, we can say. This chlorine is attached to this carbon, number 1 carbon. It is second carbon. It is third carbon. It is fourth carbon. So here it is 1,4 dichlorobenzene. This also called what in the sense para dichlorobenzene like this. This is a 1,4 dichlorobenzene. 1,4 dichlorobenzene, para dichlorobenzene, or P we can say like this. So these three, in these three, how the dipole moment will be there, that we will see. How the dipole moment in these three molecules. Okay. Now we will take a here. For this dipole moment is what? For this bond, what is the dipole moment? Here carbon atom present, here chlorine atom present. Chlorine is more electronegative than this carbon. Therefore, this bond is having dipole moment like this. This bond is having dipole moment in this way. Okay. So this bond is having dipole moment in what way we said? This bond is having dipole moment like this. This bond is having dipole moment like this. So for this bond dipole moment, is remaining same. So what is the resultant dipole moment we have to consider? For these two bonds, what is the resultant dipole moment we have to consider? Remaining are CH bonds. CH bonds we need not consider. Okay. And we have to mainly consider CCl bonds. CH bond also, whether we have to consider or we should not consider, that also we will see it. Then we will come to this one. Okay. For which we will take benzene, we will take. Benzene formula is C6H6. For this, we will see the dipole moment. Then we will go to that ortho dichloro. This we will go. Okay. So benzene we will take. Benzene, we know that benzene is this. This is the benzene. In the benzene, 6 carbon atoms are there. The 6 carbon atoms present in a cyclic form. 6 carbon atoms present in a cyclic form like this. Then each carbon is having one nitrogen. Each carbon is having one nitrogen, we can say. So, like this is there. Then pi bond is distributed equally to all the carbon atoms. Pi bonding electron cloud. 3 pi bonds are there. 3 pi bonding electron cloud is distributed equally to all the carbon atoms. Now, this carbon is having 3 sigma bonds and pi electron cloud. For this 3 sigma bonds in the sense sp2 hybridization, so trigonal planar. Similarly, all other atoms also, all the carbon atoms coming under sp2 hybridization, trigonal planar. That means all the carbon atoms and hydrogen atoms present in a plane, present in one plane. Pi bonding electron cloud present above and below the plane. Sir. Now, what is the dipole moment? That we will see. Okay. Now, for this carbon is electronegativity 2.5, hydrogen 2.1. Therefore, bond dipole moment towards carbon. for this also towards carbon. Okay, if we join these two, how it will come in the sense it is 180 degree. It is 180 degree. Okay, so this dipole moment and this dipole moment are equal. This bond dipole moment, this bond dipole moment are equal. So what is the resultant dipole moment for this? What is the resultant dipole moment? Resultant dipole moment for these two bonds is 0 because it is 180 degree. It is 180 degree. Like this is 180 degree. For these two bonds, resultant dipole moment is 0. This is 180 degree. For these two bonds, resultant dipole moment is 0. Therefore, this molecule is having net dipole moment 0. Therefore, this molecule is a non-polar molecule. Therefore, benzene is a non-polar solvent, whereas water is polar solvent. Water is polar solvent, but benzene is a non-polar solvent. Why? Because for this dipole moment is 0. For this molecule, dipole moment is 0. Therefore, it is a non-polar solvent. Benzene is non-polar solvent. Okay. Let us replace one hydrogen by Cl. So now we have replaced one hydrogen by Cl. Therefore, it is having dipole moment. Okay, this bond is having like this. That means one hydrogen is replaced by Cl beside. Now we have replaced like this. So this is having dipole moment like this. So this dipole moment and this dipole moment will not get cancelled, no, isn't it? Therefore, this is having dipole moment. This molecule is having dipole moment. Therefore, this molecule is having dipole moment means this molecule is having polarity because of this CCl bond. Okay. Now, like this. Here, two CCl bonds are there. Two CCl bonds are there here. It is on CCl, it is on CCl. Two CCl bonds are there. What is the resultant dipole moment? For this, we want the angle we want. So, what is the angle in the sense? This angle is 60 degree. So, we know the angle, so we can find the resultant dipole moment for this. So, for this, we want angle. What is the angle here? This angle is how much in the sense? 120 degree. This you know that this angle is how much in the sense? 180 degree. So from this we can find a dipole moment. We can find now this orthodichlorobenzene dipole moment is 2.54 dB. Metadichlorobenzene dipole moment is 1.48 dB. This paradichlorobenzene dipole moment is 0. For this dipole moment is 0. This is having less. This is having somewhat higher. It is having still higher. Okay, because here angle is 60 degree. Here 120 degree. Here 180 degree. So ortho, meta, para. How they are having dipole moments that we have seen. Okay, this is about dipole moment. Then using this dipole moment, what we can say whether the molecule is polar molecule or non-polar molecule we can say. Set. Next, using dipole moment, can we find what is the nature of bond? That we will see. Can we find what is the nature of bond using dipole moment? That point we will see. So, for which let us take an example. HF molecule we will take. HF molecule we are taking. We have taken HF molecule. Here we are going for the assumption. What is the assumption in the sense bond pair is completely shifted. Bond pair is completely shifted to fluorine. Bond pair is completely shifted to fluorine. It is the assumption we have taken. That means this bond pair is completely shifted to fluorine like this. So hydrogen fluoride will write the bond pair is completely shifted to this. Bond pair is completely shifted to fluorine. Okay. Now we can say that this HF molecule we have taken here. Before this HF molecule, here we will see that this ortho meta para we will see once more. Here we will see that bond angle. Here bond angle is how much in the sense 60 degree will come here. This 60 degree bond angle, if we consider 60 degree bond angle, here Cl, larger chlorine atoms are closer. Therefore, repulsion will be there. Though repulsion is there, this angle will be 60 degree only. Why? Because we have to see some other factors also there. That is that we will see later. So you consider that here bond angle is 60 degree, here 120, here 180. Okay, some other factors also there that we will see later. So now we will see. Now we have taken this HF molecule. In this HF molecule, we will assume that bond pair is completely shifted to fluorine. So why we have to consider like this? For what sake we have considered in this way? That means uh, HF molecule is having what nature? In order to know that, we have considered like this. Okay, HF molecule is having what nature? In order to know that, we have gone for this assumption. Okay, bond pair is completely shifted to fluorine. That is the assumption. That means hydrogen has lost one electron, so hydrogen is getting exactly plus one. Okay, so here what is assumption? Hydrogen has lost an electron completely. Hydrogen has lost an electron completely. Therefore, hydrogen plus one. Fluorine has gained. Fluorine has gained an electron. Fluorine has gained an electron. Therefore, fluorine minus one. Okay. If we give like this, if that means for hydrogen complete loss, for fluorine complete gain, if then hydrogen will have exactly plus one, fluorine will have exactly minus one, then HF has 100% ionic nature. HF has what nature? Means 100% ionic nature. Okay, sir. This is a, we are saying as per assumption. Well, actually, what is the nature of HF molecule? We do not know. That we have to find it. We have taken assumption here. Okay. Now we will go for a, now what is the dipole moment for this bond? For this 100% ionic nature means what is the dipole moment? That we will find. Dipole moment is equal to charge into bond length. Dipole moment is equal to charge into bond length. Let us substitute charge. Charge is how much? Plus 1. Otherwise minus 1. Plus 1 means relative charge. What is the actual charge? 4.8 into 10 to the power of minus 10 ESU. 4.8 into 10 to the power of minus 10 ESU, electrostatic unit. We have substituted charge. Then we will substitute this bond length in centimeter. Bond length we have to substitute in centimeter. We have to substitute. We can get dipole moment. That means calculated dipole moment we got. We got calculated dipole moment. Sir, this calculated dipole moment says that this HF is having 100% ionic nature. Okay. As per this calculated dipole moment, this HF is having 100% ionic nature. Now we will see this molecule, HF molecule, actually will have dipole moment. No? That we will take it as experimental dipole moment. This HF molecule, actually it will have dipole moment. No? That we will take it as experimental dipole moment. Now we will take a experimental dipole moment. Experimental dipole moment means actual value. Okay, this calculated means we have assumed that this hydrogen is having exactly plus one. Like this we have assumed and we have proceeded. Okay, so it is calculated means wantedly we have done. Okay, sorry, actual value is what? Experimental value. Experimental dipole moment. Okay, so calculated dipole moment is having 100% ionic nature. So experimental dipole moment says that what is the percentage of ionic nature. Okay, therefore percentage of ionic nature is equal to this experimental experimental dipole moment by calculated dipole moment into 100. This is a percentage of ionic nature. So percentage of ionic nature is equal to experimental dipole moment by calculated dipole moment into 100 we can say. Okay, so percentage of ionic nature is equal to what we can say? Experimental dipole moment by calculated dipole moment into 100. So using this formula we can find the percentage of ionic nature. Okay, experimental dipole moment means the for the given molecule what is the dipole moment actually. Okay, this calculated dipole moment means what? We have to assume that the molecule is having 100% ionic nature. This calculated dipole moment we have to calculate it. How to calculate it? by assuming the molecule is having 100% ionic nature, and we have to calculate dipole moment. Okay, sir. So this calculated value we have to do it. Experimental value is actual value. Using these two, we can say what is the percentage of ionic nature in a molecule. If you know percentage of ionic nature, then remaining percentage is called covalent nature. So we can say what is the percentage of ionic nature and covalent nature of a molecule. We can say, sorry, okay. So next we will see. Next we will take now observed dipole moment. Observed dipole moment in the sense experimental dipole moment. Observed dipole moment is equal to 2 into bond moment into cos theta by 2. Okay, observed dipole moment is equal to 2 into bond moment into cos theta by 2. Bond moment in the sense dipole moment of a bond. Dipole moment of a bond. This theta in the sense bond angle. This theta in the sense bond angle we can say. Therefore, observed dipole moment is equal to 2 into bond moment into cos theta by 2. Set. So using this also we can find experimental dipole moment. This bond moment means a dipole moment of a bond. Dipole moment of a bond is known, bond angle is known, then we can say experimental dipole moment. This experimental dipole moment we can substitute here. Calculated dipole moment we are doing by assuming that 100% ionic nature. From that we can find the percentage of ionic nature. So, if you know dipole moment, we can find the percentage of ionic nature like this. Suppose dipole moment is not given, but electronegativity value is given. That means electronegativity of fluorine is given, electronegativity of hydrogen is given. What is the percentage of ionic nature of this bond? That is asked. Then how to find? That we will see. So now we will see percentage of ionic nature. Percentage of ionic nature of bond is equal to 16 into electronegativity of atom A minus electronegativity of atom B. A and B are bonded. AB is a molecule. Between A and B, bond is present. Plus 3.5 into electronegativity of A minus electronegativity of B whole square. Okay. A is an atom, B is an atom. Between them, bond is there. AB is called molecule. XA is called electronegativity of A. XB is called electronegativity of B. Okay. If you know the electronegativity values, then we can find percentage of ionic nature. If you know dipole moment, then we can say percentage of ionic nature. So percentage of ionic nature is said using dipole moment, otherwise using electronegativity values set. Okay, these about dipole moment. Okay, next we will see about intermolecular forces. Next we are seeing about intermolecular forces. Intermolecular forces. Intermolecular forces in the sense between two molecules, what is the attractive force? That is called intermolecular force. So between two molecules, what is the force of attraction? That is called intermolecular force. Okay. In this, many types are there. That is that many types in the sense that depends on molecules. Okay. Now we will take one example. We will take helium. Helium is a gas. In the normal condition, helium exists as a gas. Sir, we can liquefy this helium gas into helium liquid. Helium liquid. At which temperature? In the sense at 4.4 Kelvin. Even it can go to 2.2 Kelvin also. Helium, it is in liquid state only. But a difference is there. Between them, difference is there. So anyhow, helium gas we can convert into helium liquid. Sir, we can convert helium gas into helium liquid in the sense between helium molecules, will there be any force of attraction or not? You think it? Gas is converting into liquid means what? Molecules are coming closer, that's why gas is converting into liquid. What is the difference between gas and liquid? Gas means molecules will be far away, liquid means molecules will be closer. Solid means molecules will be still more closer. Gas is converting into liquid means molecules are coming closer, that's why gas is converted into liquid. Why molecules are coming closer? because of attractive force between the molecules. That attractive force is called intermolecular force of attraction. Sir, how attractive force is created between helium molecules? That we will see. Between helium molecules, attractive force is created. Attractive force is there. Due to attractive force, gas is converting into liquid. So what is the attractive force? How that attractive force is created? That we will see. Now we will take helium. For helium, we will consider nucleus. It is a nucleus. Helium electronic configuration is 1s2. 1s2 in the sense symmetric and spherical. 1s2 in the sense symmetric and spherical. Okay. This 1s2 in the sense symmetric and spherical. Okay. This 1s2 in the sense this electron cloud is present here. Okay. So here what is present in the sense electron cloud is present. Okay. So here the electron cloud is present in this manner. Electron cloud is present. Electron cloud is present. Another helium we will take for that nucleus, and that is also having 1s2 electronic configuration. 1s2 electronic configuration, symmetric and spherical. Symmetric and spherical. What is symmetric and spherical? That point we will see. Now, here we will take this side, we will take 1 point. This side we will take 1 point. From here to here is called radial distance, or from center of nucleus to this point, radial distance r. Okay. Now we have to consider radial distance remains same. Radial distance remains same for these 2 points. Okay. For these 2 points, radial distance is same. Theta can be any value. Phi can be any value. We need not make them as same. Theta and phi, we need not make them as same. It can be any value. If you want to take this point this side, you take it. That's why I said theta can be any value, I said. Phi can be any value, I said. But radial distance should remain same. Then for this point chi square, for this point chi square is equal. Therefore, one is symmetric. Okay, so why it is this oneness 2 is spherical in the sense shape. Okay, symmetric in the sense this is the point. When radial distance is same, chi square remains same at whatever the theta and pi value set. So for helium, the electronic configuration is 1s2. For this helium also, the electronic configuration is 1s2. Sorry, okay. Now this is what in the sense a symmetric electron cloud. Electron cloud is symmetric. Here also electron cloud is symmetric. Okay. Now at any one instant, why we have to take any one instant in the sense this is said as electron cloud. This 1s2 means this helium is having 2 electrons. The 2 electrons present in the form of cloud. You might have seen that naturally you might have seen that water vapors cloud you can see in the sky. That clouds, if you see, is it taking constant shape? That cloud will not take constant shape continuously. Cloud shape will vary from one time to another, and also it will move continuously from one place to another place. It will not stand at constant place. It is superficially like this happening. So, that word is given for this electron. That cloud word is given for this electron means this electron cloud also is not taking constant shape. Superficially we are talking. Constant shape it is not taking. It is not present constantly at one place. That is the meaning. That's why here cloud is given. Therefore, what will happen here? That we will see. Now, this helium at a given instant, what happens means it is a nucleus. The electron cloud comes like this. Okay, at a given instant for this helium, what happens means the electron cloud becomes like this. This side probability of electron cloud becomes high. This side probability of electron cloud becomes low at a given instant. This is taking place to what in the sense very least extent, that's what we can say, very least extent this difference is very least, not much. This difference is very least and not much, and also at a given instant only, it is not permanent. This is we said here, this side in this helium nucleus is there, this side probability of electron cloud is high, this side probability of electron cloud is less, we said it is for a given instant, it is not permanent, it is not constant. Okay, if it is permanent in the sense, why to say this is helium is 1s2 configuration, s orbital is spherical and symmetric, why to say, isn't it? Okay, so here probability of electron cloud is high, here probability of electron cloud less, in the sense this symmetric arrangement, this symmetric electron cloud is get distorted at a given instant temporarily. Okay, so but after once we said it is symmetric, then why do we say like this, why do we say getting distorted? If we say this one, if we consider like this, then only we can explain this liquefaction of helium gas, otherwise no. Liquefaction of helium gas in the sense, we are cooling this helium gas below room temperature, and we are taking this helium gas to what temperature, 4.4 Kelvin, in the sense how much disturbance we are giving externally, you have seen this much disturbance we are giving, then why can't this symmetric electron cloud gets distorted? Therefore we can consider. Okay, so this symmetric electron cloud gets distorted here, therefore this side probability of electron cloud is high, this side probability of electron cloud is less. This is a temporary only, and it need not be constant. Okay, so this side electron cloud probability high, in the sense this side gets a partial negative charge, this side probability of electron cloud is less, in the sense this side gets a partial positive charge. Okay, so this side partial positive charge because less electron cloud probability, this side partial negative charge because high electron cloud probability. Okay, now for this helium, though it is having 1s2 configuration, symmetric and spherical, it is also having one end pole and one end another end negative pole, therefore it is called a dipole. This dipole is created instantaneously, therefore it is called instantaneous dipole. This instantaneous dipole is possible for which type of molecules, in the sense only for non-polar molecules. Non-polar molecules, in the sense net dipole moment is 0. For those molecules only instantaneous dipole is possible. Therefore, if non-polar molecules is having net dipole moment 0, for which instantaneous dipole is possible. Okay, for polar molecules we need not consider this word. This word is mainly for non-polar molecules for which dipole moment is 0. That means they are symmetric. Okay, sir, this is a temporary, understand that it is temporary, so we got instantaneous dipole, we got, sir. So for helium we are considering instantaneous dipole, instantaneous dipole we are considering for helium. For helium we have considered instantaneous dipole. Okay, this side partial negative charge, this side partial positive charge. Now we will take another helium atom, we will take. Now we are taking another helium atom. Okay, it is another helium atom. For this helium atom, it is symmetric and spherical. It is symmetric and spherical. Okay, this is what in the sense symmetric and spherical. Symmetric and spherical. Now what will happen here? That you see that this negative charge. This negative charge induces this atom. This negative charge. What this negative charge does means this negative charge. This negative charge repels this negative charge, okay, due to that what will happen, this negative charge, this partial negative charge is repelling this negative charge because electron cloud. Because of that, this electron cloud is migrating this side. This electron cloud is migrating this side. This electron cloud is migrating this side. Therefore, this symmetric arrangement is getting distorted. This symmetric arrangement is getting distorted. Therefore, it becomes like this. So this side, what happens? This side probability of electron cloud becomes high. This side probability of electron cloud becomes high. Whereas this side, how it will be there means probability of electron cloud becomes low. Probability of electron cloud becomes low. This side probability of electron cloud becomes low, whereas this side probability of electron cloud becomes high. Okay. Therefore, here electron cloud probability high, therefore partial negative. Here electron cloud probability less, therefore partial positive. Therefore, this is becoming dipole. This is becoming dipole. This dipole is created because of this. This dipole induces this dipole. This dipole induces this helium atom to become dipole. Therefore, it is called a induced instantaneous dipole. It is induced instantaneous dipole. Why instantaneous? It is temporary. Because of this one only it is got like this. Otherwise, it will convert back to symmetric. It will be in symmetric only. Okay. It is induced instantaneous dipole. It is temporary only. This is temporary means it is also temporary only. Now we got instantaneous dipole, induced instantaneous dipole. Now see, this partial negative charge will attract this partial positive charge, yes or no? Therefore, between this instantaneous dipole and induced instantaneous dipole, attraction is possible or not? Because here partial negative charge is there, here partial positive charge is there. This positive and this negative will attract with each other. That means between this instantaneous dipole and induced instantaneous dipole, attraction is there or not? Attraction is there. This type of attraction is one example for one type of intermolecular force of attraction. So in the intermolecular force of attraction, one type is called what means instantaneous dipole, induced instantaneous dipole. This is called van der Waals force of attraction. This is possible for which molecules? Non-polar molecules. So for non-polar molecules means dipole moment is 0, for which what is the intermolecular force? Van der Waals force. That van der Waals force means what? Instantaneous dipole, induced instantaneous dipole. Sir, now we will say this force is possible for which case? This force is possible for which case, that we will see. This instantaneous dipole, induced instantaneous dipole, this force of attraction is possible for which case means non-polar molecules. Non-polar molecules means all the noble gases. Okay, methane is non-polar molecule, CCl4 is non-polar molecule, BeCl2 dipole moment 0, BF3 dipole moment 0, like this we can say. Okay, sir. Next, here interaction energy. Interaction energy in the sense force of attraction between molecules. Okay, interaction energy is directly proportional to 1 by r power 6, where r is called distance between two molecules. Where r is called distance between two molecules. R is called distance between two molecules, we can say. Okay, so interaction energy in the sense intermolecular force of attraction, that is directly proportional to 1 by r power 6. R is called the distance between two molecules. This is for this van der Waals force, this instantaneous dipole, induced instantaneous dipole. For this force of attraction, this is the formula we can use. Okay, now we will go for next type of intermolecular force. So for which type of intermolecular force we have discussed? Van der Waals force. That means instantaneous dipole, induced instantaneous dipole, that force of attraction we discussed. That is for which? Non-polar molecules. Non-polar molecules means what is the dipole moment? 0. Non-polar, this van der Waals force is temporary or permanent? Temporary. Okay. Next, we will go for next type of intermolecular force, that we will see. Now we will take what is a molecule in the sense HCl we will take. I am taking HCl. In this HCl, this hydrogen is having partial positive charge, chlorine is having partial negative charge. We know because electronegativity difference is there. Therefore, this bond is polar bond. This molecule is polar molecule. This molecule is having dipole moment. In this molecule, one end is having partial positive charge, another end is having partial negative charge. Therefore, this molecule is a dipole. Another HCl will take, in another HCl also partial positive, partial negative. It is also dipole. Okay, it is also dipole. Between this dipole, is there any attraction or not? Means this partial negative charge will attract partial positive charge. This attraction is called dipole-dipole attraction. Okay, this dipole-dipole attraction is another type of intermolecular force of attraction. So for intermolecular force of attraction, another type is what? Dipole-dipole force. Dipole in the sense, this is polar molecule. For polar molecule only dipole is possible. Polar molecule means a dipole moment is there. Okay, it is polar molecule, therefore this dipole will exist permanently. Therefore dipole-dipole attraction is a permanent. Okay, permanent. It is possible for which molecules? Means polar molecules. Okay, so here what type of intermolecular force? Dipole-dipole force. Dipole-dipole force. It is possible for which? For polar molecules. For polar molecules it is possible. For polar molecules, what is the dipole moment? Not equal to 0. Okay, so for this it is possible. Example is CH3Cl. It is having dipole moment. PCl5 is example. Water is example. These are polar molecules. For polar molecules, dipole-dipole force of attraction is possible. Okay, in this case, interaction energy is directly proportional to 1 by r cube. It is for a what means solid, r in the sense not radius, distance between two molecules. Okay, next, interaction energy is directly proportional to 1 by r power 6 for which molecules? In the sense, for rotating molecules. For rotating molecules, we can say like this: interaction energy is directly proportional to 1 by r power 6 for rotating molecules, we can say. Sir, next we will take, now we will consider what? In the sense, let us pass noble gases. For example, let us pass helium gas into water. Let us pass helium gas into water. So what will happen? Helium gas dissolves to some extent. Okay, if we are passing helium gas into water, what happens? Means helium gas dissolves in water to least extent because solubility is very low. That's why it is dissolving in water very low extent. Okay, in water dissolved air will be there. Air is containing helium, but that amount is very low. Okay, now helium gas is dissolved in water to least extent. Okay, now we will consider water. In water, oxygen is the central atom and two hydrogen atoms are there. This oxygen is having two lone pairs. This water is having dipole moment. Okay, this water is having dipole moment. How that dipole moment is there, that we will see. This bond is having dipole moment towards oxygen. This bond is having dipole moment like this. Now for this lone pair, dipole moment towards up. For this lone pair, dipole moment towards up. That means what is the net dipole moment? Net dipole moment for water, that we'll see. What is a net dipole moment for water? Okay, so net dipole moment for water is projecting towards up. Net dipole moment for water is projecting towards up. Positive end is where? Means hydrogen. Negative end is towards oxygen. Okay, next, now we will give for water. For water we are giving like this: oxygen is more electronegative, hydrogen is less electronegative. So for hydrogen, partial positive; for oxygen, partial negative. Okay, now these two ends are having partial positive charges. What is the center of positive charges? Okay, for these two, what is the center of positive charges? That we will take center of positive charges in the sense